Okay.
She will,
Hello. Sorry.
She will give a talk about large terms in brane-antibrane inflation. Please.
Yeah, thank you. Hello, everyone. I'm Dibya from University of Puebla. So first, I would like to thank the organizers for giving me the opportunity to present my work today. So today's work will be based on these following articles. Can you all see my pointers on the screen?
Yes.
Okay, so my today's talk will be based on these following articles, where one of them is already done and the other one is a work in progress. So these are the works done in collaboration with Roberta Cioffoloni, Oscar Loaiza, Gustavo Nis, and Yvonne Zavala. So let's start. Oops. Okay. So we already know that the current understanding of our universe is currently based on a phenomenological standard model of cosmology known as lambda CDM. Various cosmological observations have established this model, and where lambda stands for dark energy and CDM stands for cold dark matter. Now, besides its phenomenological success, this model has a flatness and horizon problem, which can be circumvented, if one allows an early period of accelerated expansion known as inflation, or I should say, accelerated period of exponential acceleration. Now, besides inflation, besides solving those problems, that is the flatness and horizon problem, it can also give us the seed for the structure formation that we observe today. Now, besides all that, we also know that our universe is also now in a currently accelerated state, sourced by the dark energy. Now, now we should talk about the inflation for a minute. Now, the inflation for it in its minimal structure is where a scalar field minimally coupled to the non-minimally coupled to the gravity rolls down a scalar potential, where the inflation happens when the scalar field is rolling along this flat plateau or this quasi-flat plateau of the potential, and inflation stops when it rolls down the potential. That is where the kinetic energy takes over. So inflation happens when the potential energy is dominating over the kinetic energy. Now, when and where inflation stops can be computed by or determined by the slow roll conditions and the slow roll parameters, the well-known slow roll parameters epsilon and eta. Now, the predictions coming from the inflation, that is on the primordial gravitational wave, are right now tightly constrained by the various cosmological observations, such as Planck. Now we can this picture on this this picture where I'm pointing the pointer is the result by the Planck collaboration, and we can see that the predictions from the single field models of inflation are fairly consistent with the data. And the y-axis is the tensor to scalar ratio, and the x-axis is the primordial tilt, all the spectral index. Now, if these models, if the single field models of inflation are currently consistent with the data, then why should we look beyond, or why should we go beyond the single field models of inflation? Well, there are various reasons. Let us look at them one by one. So the first one will be that we know that the inflation happens in a such high energy scale that one may naturally lead to thinking that inflation may be consistently embedded in a quantum theory of gravity due to its high energy. And and now we know that on these quantum theories of gravity, there are recently proposed the quantum gravity constraints, which are actually putting tight bounds on the single field models of inflation. Those constraints are the well-known Swampland conjectures by these authors recently, and they are fairly recently proposed, and there are many of them. Sorry. Now, next, there are another reasons, or there are another motivations to study all these models of inflation. There are many, but one of them could be, we can think of the formation of the primordial black holes, or the features in the power spectrum, which can be obtained in presence of if you have inflection points on your potential or bumps in your potential, and those can be obtained in the single field models of inflation. But the problem is it requires severe fine tuning. And why should we study those primordial black holes? It's because the black hole merging events that we observed in the LIGO Virgo, or the high amplitude peaks that we observe in the nanograph signals, so those primordial black holes can act as the progenitors. So if we want to study them in the single field models of inflation, then it requires severe fine tuning, like I said before. Now, this quantum gravity origin, I mean, if we have to go to the quantum gravity origin due to its high energy scale of inflation, we know that those in the theory of quantum gravity, there are plethora of scalar fields. There are many various scalar fields available. So why should we necessarily constrain ourselves to the single field? So now we know that the quantum gravity is a huge domain. It offers a huge domain, and there are many areas to look at. So we should know where exactly we should direct our. We should direct towards. So string theory, as a leading candidate of quantum gravity offers the toolkits which can be used to study the microphysical understanding of the effective field theory that drives our universe. So within that string theory, there are multiple fields, and one can naturally relate to study the multi-field models of inflation, such as the one given here. And not only multi-field, the multi-field which features large turns or the non-geodesic trajectories in the field space, or there are modulation available at the level of the potential. So, and those can be interesting to study the primordial black holes, the induced gravitational waves, and many others. Such as the works done by these collaborations. Now, currently for this work, our goal is to study the simplest or the oldest model of string inflation, known as the brane-antibrane inflation, or to be precise, D3 anti-D3 brane inflation. Now, let me give you a synopsis of how this the simplest model of the brane inflation, or how the brane inflation works. So in the string theory, in the supersymmetric superstring theory, one starts from the 10 dimension and dimensionally reduce on a Calabi-Yau to get to the point of the 4-dimensional effective field theory models. And at that level of this 4D, there are various scalar fields, like I have also mentioned before. And those scalar fields are mainly related to the size and shape of this extra dimension. Those will be closed string, those are the scalar fields sourced by the closed strings. And there can be also another type of scalar fields, or the moduli, which are related to the position coordinates of the d branes in the internal space, which we are mainly interested in this talk. So, those are the scalar fields. Now, we have to stabilize those scalar fields. And how do we do that? We turn on the fluxes in our internal space. And those fluxes do two things. So one is to stabilize those scalar fields, and second, it backreacts on the geometry, creating this warp throat like geometry, or locally creates this warp throat like geometry, especially known as the Klebanov-Stassel throat. Now, here I'm showing one explicit metric which will be useful for this talk. And usually when you have warping, and when you consider warping, you write down this type of metric, where this is the 4D part, this is the 6D part, and H is the warp factor. However, the D-brane model, the D-brane inflationary models are usually plagued with challenges, such as the moduli stabilization. So to be very honest, when one considers the D-brane model of inflation, or D3, D5 model of inflation, one kind of assumes that the other moduli, such as this complex structure or the Kähler moduli, which is related to the size and shape of this extra dimension, they are already stabilized by the fluxes we turn on. But we do not explicitly add them in the contribution at the level when we write down the scalar potential or do the cosmological evolution. They do not affect the geometry. They are kind of the two separate regime. And last but not least, and there are also problems with the observations. Some models are raise questions. And lastly, the models also features eta problem, which we now see. Now, these eta problems are related to the mass of the inflation, that is the mass of the inflatants, Now, until recently, it has been assumed, or it has been shown, that eta problem is eta problem is one of the main problems hindering both the single field and the multiple models of inflation in supergravity. Now, until recently, we have shown that eta problem can be successfully circumvented if one allows a large turn in the field space. Now, in the standard law, one can see that in the standard law, one usually assumes that either all of the scalar fields are lighter than the Hubble parameter, the underlying Hubble parameter, or one of them could be heavy. In this fat inflation, where we have done in collaboration with these authors, we have shown that that doesn't necessarily has to happen. So one can have the mass of the inflatants heavier than the Hubble parameter, but one can still get a successful period of inflation if and only if there is large turns in the field space. So we have studied this such fat inflation. We call this fat inflation. Now, we studied this fat inflation in an explicit model of D5 brane, where there is a 5 brane extending along the 4 non-compact dimension, that is our space-time, and wrapping 2 times an internal space in this local geometry of this Calabi-Yau, which is known as the warp resolved conifold, WRC. Now, we have computed the potential, and we have seen that the potential takes effectively the shape of a natural inflationary potential, and this is how the potential looks like. And we have computed, we have done the scalar, we have computed the equation of motion, and we have done the cosmological evolution of the scalar fields, the 2 fields, the radial and the angular, along the radial field and the angular field. And we have seen that the R and NS that I was showing earlier, this spectral till and the spectral index, the prediction coming from this fat inflation are significantly deviating from the single field models of the prediction from the single field model. So this cyan dashed line is the prediction from the fat inflation, and this orange continuous line is the single field models of natural inflation, to be precise. Besides, we have also computed the non-Gaussian parameters, and we have seen that the predictions from the fat inflationary model is significantly deviating from the single field consistency clock. Next, let us start with the potential for the D3 brane, or how to derive the potential for the D3 brane that we are mainly interested in. So in the origin for the potential for the D3 brane comes from 2 types of sources. So one is because this D3, first let me tell you how the D3 brane inflation happens. So the D3 anti-D3 brane inflation takes place when this this probe D3 brane makes its journey from the UV towards the IR, where there is an anti-D3 brane sitting at the tip. And since the D3 brane and anti-D3 brane, they have opposite tension and the charges, they are attracted towards each other via Coulomb interaction. So the origin for the potential between the brane-antibrane comes from the 2 sources. So one will be the Coulomb interaction. Due to the Coulomb interaction, so it will give us the Coulomb force, Coulomb potential. And the next is from the supergravity origin. And how does that appear? It's because when this local throat-like geometry, what one does is that first one considers this local throat-like geometry, such as the Klebanov-Strassler throat or the deformed conifold, which I will mention shortly. So first one considers this local structure, and then in order to make it compact, one glues this local structure back at the Calabi-Yau. So first one cuts it and then glues it back to the whole Calabi-Yau to make it a compact geometry. So the next contribution to the potential comes from this gluing procedure. So first, in order to compute that, one usually starts from this dBi and Chern-Simons action, where one writes down that this is the dBi part and this is the Chern-Simons part. And the potential takes this form where exponential 4a is the inverse of the warp factor, and a, where this a and alpha, that depends on the radial coordinate of the internal space. And I should mention that we have considered specific answers where this probe brane moves along one radial direction and one angular direction of this deformed conifold. And what is this deformed conifold? It is the local structure that I was talking about. Due to the presence of warping, one gets the cavernous strata type throat, and locally it looks like a deformed conifold, or in presence of fluxes we should say warped deformed conifold. And here I am showing the unwarped metric of this deformed conifold, where eta and tau should have the same meaning, so they are both the radial coordinate, and g1, g2, g3, g4 they are all dependent on the angular coordinates, the five angular coordinates. The supergravity field equations looks like this, where R4 is the four-dimensional Ricci scalar. Lambda comes from the fluxes that used to stabilize the moduli. So lambda is the G3 fluxes of type 2B string theory. And these are the local terms, and this is another terms which doesn't necessarily contribute. This term depends on the warping. And there are local terms where the first source, that is the Coulomb interaction, sits here. So local terms will be the Coulomb interaction between the anti-D3 and D3 brane. Now let us see one by one. So all of them contributes to the final scalar potential, and due to this contribution, usually one gets the angular dependency at the level of the scalar field. So here it's the first one is the harmonic part of this Laplace equation. So lambda, where this nabla square is the Laplacian computed from this unwarped deformed conifold here. And R4 is the Ricci scalar, and when we have the non-vanishing Ricci scalar in the de Sitter space, then it will gives us a mass term. It will look like a mass term because it will have lambda square, tau square, the radial coordinate square. So this will give us a mass term, and the contribution coming from this fluxes and this homogeneous part, both of them gives us a potential which depends on both tau and theta. I mean both the radial and the angular coordinate. Now, the full potential features both, full potential consists of both this D3 brane potential and the Coulomb potential. So the Coulomb potential will take the following form, where lambda phi UV is related to this tau UV, where tau UV is, So the tau UV is where you glue the throat back to the Calabi-Yau, where after the cutting, you have to glue it back, right? So it denotes the radial length where you glue it back to the Calabi-Yau. Yeah. And T3 is the D3 brane tension, and D0 depends in the following way, where H inverse is the warp factor inverse, and X here depends, it's a dimensionless parameter, which is given by tau UV, which is tau is the radial coordinate again. So the full brane potential is necessarily all the contribution taken together. Where remember that the theta contribution, the contribution coming from theta only comes from when you take into account the UV deformation. So when you glue it back, so their contribution coming from there, at theta will be generated from there. The potential in terms of theta. Now we have, the potential, after doing all these computations, so they will give us like a form of the potential, which will depend on the hypergeometric functions and various other harmonics. So doing all that, you will get a potential which depends on obviously both lambda, tau, and theta, and they will effectively take this form where 1 over tau is the radial coordinate. It has a negative 1 over tau to the power 4 behavior, which will become important when this D3 brane will move towards the will move towards the tip of this warp throat. And this part is totally coming from these this harmonic part and the flux part of the scalar potential. So they will feature a type of potential which will be polynomial in both Fi and Gi. And there will be trigonometric function, but if one takes a series expansion, they will become polynomial. And F tau, like I said, F tau depends on the tau to the power n. And n can be both integer and non-integer. Now the potential features a saddle, so there is a minimum along the theta direction, but there are none along the y direction, the radial direction. And if you consider the cosmological evolution of the fields, they give us such behavior. So where the field starts rolling from here, and then it takes a bend, or it takes a kind of bending structure, and then goes towards it just rolls away towards the zero in this case. And where the inflation should stop, because there is nothing beyond the zero along radial direction. Next, following these authors, that is De Wolf, McAllister, Shue, and Underwood, we have found that there could be the Coulomb interaction. The Coulomb interaction, like I have written here, it features only the angle, the radial coordinate, right? But there could also happen another scenario where this Coulomb interaction happens between the angular coordinate of both brane and antibrane, which will feature just another piece to the full potential, which depends on minus 1 over theta to the power 4. So now, if that is the case, then the field evolution slightly changed, and it does a different kind of bending in the field equation of motion, or the field space trajectories. Now, for there is a third possibility which arises when one considers the dBi inflation. That is, when the branes are the brane motion are relativistic. We have been only considering, up to this point, we have been only considering, including the fat inflation, our branes were non-relativistic. And here, if we consider the relativistic, I mean, the brain has relativistic motion, especially along the, I mean, it could be either angular or radial direction. So then if we consider that, then the potential features the global minimum, which is good to study the inflationary geometry because of the reheating in mind. But the problem is this potential is too steep. So it is currently a work in progress. So we want to see if we can make this potential shallower to study inflation at this point. Next, one can now, all this potential that we have studied, and I have also explained earlier that our motivation is to study features in the power spectrum, or we want to see if there could be non-trivial turning rate in the field space, which is not studied earlier, which have not been studied earlier. So we want to study that. So there is an analytical way to study or to get the non-trivial turning rate in your field space, which could be like this. So one can write down the L kinetic, that is the Lagrangian for the kinetic part. So this will feature, I mean, this will be nothing but the metric, the field space metric. So AFX will be the field space metric along the radial coordinate, and AGX will be along the angular coordinate. So having done that, I mean, having considered that, if you write down the field equation of motion, that is the usual scalar field equation of motion, Klein-Gordon, then you can write down, I mean, you get the following form considering this metric and computing all the Cristobal symbols. So on top of that, if you impose a condition that is r prime equal to 0, and note that it is not theta prime equal to 0, because theta prime equal to 0 will give us a geodesic motion, and we are after a non-geodesic, we are chasing after non-geodesicity in the field space metric. So if we impose r prime equal to 0, then omega over h can give us a concise formula, and tuning the same, we can get the non-trivial turning rate in our field space. Now there are some challenges. So I mean, I have been talking about all these the potential and the deuterobrane anti-deuterobrane motion, but I haven't said anything about the turning rate that we are getting at the level of this at the level of this potential, or using those potential. So there are challenges, and because we could not find any large turns yet, and it is still a work in progress, so there are challenges that we have to overcome, or we have to deal with. Now, what are the challenges? So the challenges is because we have seen that because we are working in this deformed conifold, our the metric is too too flat, or the metric does not have any functional dependence on both r and theta, on both radial coordinate and the angular coordinate. So the value of this the curvature, the Ricci scalar of this field space is order 1, which is not great to study large turns in any model of supergravity. Then the warping disappears from the metric. So once you write down, so if you write down the dBi and Chern-Simons action, and we know that we can get the explicit form of the metric from this action directly, because it will also give us the kinetic terms, L kinetic. So we can see that this exponential Fourier, I mean, once you get rid of this square root and you expand, so you will see that this exponential Fourier will cancel this exponential minus Fourier, and we do not have the tuning that comes from the warping, because warping depends on many supergravity parameters in deformed conifold. So it gives us a lack of tuning at the level of the kinetic term. Now, what are the possible way out? So these authors have already studied one model where they have allowed modulation in the potential, or in terms of the action monodromy. So you have many plateaus and many bumps in the potential, then it can be a possible way out. Then the another one could be adding more fields. So I mean, you can imagine, so if you're studying D3 brane, so you have six, so the D3 brane has four like 4D. I mean, the D3 brane progresses around the 4 dimensions, so it has 6 scalar fields available to study. So you can so right now we are adding only 2 fields, so we can talk, I mean, we can add more fields and see if they can add something extra, like a modulation in the potential. Next, so the outlook, I mean, the way the take from this work is we want to study the primordial black holes or the induced gravitation waves, and how we can do that. We want to allow modulation in our potential, or we have to consider some other type of internal geometry that can give us some more tuning in our model. And this is already a work in progress, so tune in for my next in the archive for next couple of months or so. And thanks for your attention. I will take questions.
Okay. Thank you for giving nice talk.
Very nice question. So recently there is a discussion about swampland and landscape. So is your model stable up to the criticisms of swampland conjecture?
If I know the swampland conjecture, is that the question? Sorry, I did not hear properly.
So there are some criticisms about the swampland conjecture about quite diverse string G models. So is your model stable or safe up to the criticism of swampland conjecture?
Oh, yeah, right. So the swampland conjectures, they are mainly, I mean, the swampland conjecture, I mean, I have to use this epsilon and eta parameter. So the swampland, wait, yeah. So the first swampland, according to the first swampland conjecture, this epsilon v parameter cannot be less than 1. And for the second swampland conjecture, and I'm talking about the de Sitter swampland conjecture, because those are the two that are relevant for the models of inflation. And the second, according to the second swampland conjecture, the epsilon eta v parameter has to be the mod value of the eta v parameter has to be greater than equal to some number, minus of some number, or sorry, the other way around. Eta v has to be greater than some negative of some number, which is that the mass of the inflatants has to be tachyonic, right? So those are the two conjectures. Now those are mainly applied to the single phase model of inflation, and for the multi-phase model of inflation, I mean, I'm not writing that exact formula I don't have the exact formula in my talk, but we have shown in this paper with these authors, we have already shown that when we are considering multi-field models of inflation, the slow roll parameters get deviated from this usual slow roll parameter, that is just v prime over v. You have a term which depends on the turning rate. So if you have the turning rate and if you have the non-trivial turning rate, so epsilon v parameter can be bigger than 1, because this v prime by v can become bigger than 1. But with the help of this turning, you can have the successful period of inflation. So you can bypass the swampland conjectures in that way. And at the same time, you can also be okay, probably you can also be okay with the swampland distance conjecture, because the original swampland distance conjecture was on the geodesic field space. And we are talking about, with the effect of turning, we are talking about some non-geodesicity in our field space. So probably we are bypassing that as well. I mean, there are debates, active debates on this field, but that will be my answer. Did I answer the correctly? I mean, if I have understood your question.
Okay, thank you.
Okay, thank you.
Thank you. Okay.
Thank you.